Alright, welcome back to the last part of section 1.2, and we are going to go quickly through these graphs. These are the kind of parent graphs that you should know because we're going to be moving these things around like crazy and you got to be able to know them, okay? So first is our constant function. We've already kind of alluded to some of this with our y equal to a number. This in function form is just f of x is equal to some constant. So if I let that be c, a constant function is one that is a y equal to a number, and so that is just a horizontal line. The identity function, which is a linear function, is identified as y equals mx plus b, or in this case, y equaling x. So we have an intercept of 0 with a slope of 1 over 1. So I end up getting these points, and this right here that bisects the first and the third quadrant is the identity function. We just talked about the absolute value function when we looked at the piecewise function. So at 0, that is my vertex, and it goes with whatever the number is in front is actually the slope of that. Whoops, I'm off a little bit. Make sure you go through those points. And so that would be our parent function for our absolute value. Quadratic function. The parent function of a quadratic function is y equals x squared, or f of x equals x squared. And so if you plot some points, this is an even function in which we are symmetric over the y-axis. If I put 0 in, squared is 0, 1 squared is 1, 2 squared is 4. So this little chart here is really important to kind of get some good points. You're going to have that vertex at the origin going over 1 and up 1 gives me another point, and from the origin going over 2 and up 4 gives me another point. But if there's a 2-for-1 deal with it being symmetric over the y-axis, for 2 away here, I'm 2 away there, and what I can construct now is that quadratic function. It's a U-shape. Absolute value is a V-shape. Quadratic is a U-shaped function. If I have the square root, y equaling the square root of x, or f of x equals the square root of x, these two things are inverses of each other. So what I have now, the definition of an inverse, is that I can switch the domains and ranges of its inverse. So that means that this 0 now becomes here. So it's hard to see with the 0, 0 and the 1, 1. But if I throw in 4, the square root of 4 gives me a 2. So you can see that those points are reversed. So that kind of gives me the over 1, up 1, over 4, and up 2 gives me that function that looks like this. Now, this is a function, but if I were to complete it with a full parabola on its side, that would not pass the vertical line test. So you gotta be careful. The square root is only kind of half of a U shape. A cube, f of x equals x cubed. If we do a t-chart here with this, I kind of like you to see that -2, -1, 0, 1, and 2. And so that gets me, when I cube each one of those, that gets me -8, -1, 0, 1, and 8. So it is going to be symmetric to the origin because the opposite of x and opposite of y do appear. So 0, 0, over 1, up 1, over this way, and down 1. Then we go over 2 and up 8, which is going to be up here somewhere, and over 2 and down 8 is going to be down here somewhere. So an x cubed kind of looks like, I always call it a squiggle. Okay, so it has a little squiggle there at the origin. It is going to be symmetric over the origin. And so that is our x cubed. Now, the inverse of that, if the inverse of cubing, or the inverse of squaring is square rooting, then the inverse of cubing is cube rooting. So now I get this, and then my t-chart just reverses as the inverse. -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. And so basically now I have it on its side. So these points are actually the same. So instead of going this direction, we're going to go horizontally because now I get -8, -2, which is about here, let's say. And I get something that looks like that as my cube root function. Okay, if we had obviously a bigger coordinate plane, we could be a little bit more accurate. So, those are your parent functions, and now we're going to investigate how to transform those. So we're going to investigate with an x squared. So what would happen if I do a +1 or a -3? So if I had my original x squared and I did +1 to each of those y values, then that would just mean that I would move up 1. So the new vertex now is vertically moved up by 1. I still have over 1 and up 1, over 2 and up 4 from the original, or not the original, from the new vertex gives me those common points. So these points that I have right here, you want to make sure that you're able to do that kind of in a quick way to sketch that graph. Now, this parent graph is x squared, so it is a parabola, but with this minus 3, that means I go from the original origin, from there down to negative 3, over 1, up 1 from that point, then over 2 and up 4 gives me this one. I get a 2-for-1 deal, so I can match up those points, and I get that parabola. So what we have here to investigate our first transformation, this is a vertical shift. And so, generalizing here, we can generalize this as a vertical transformation. We're going to let f be a function and c a positive real number. Then we have y equals f of x plus c takes the original up by c, and y equals f of x minus c takes the original down by c. So you take the sign as is. That is the vertical shift that we have there. So what do we do when we look at a horizontal shift? And in a horizontal shift, now you're dealing with the x value there. Instead of what's added or subtracted at the end, it is going to be kind of grouped with your x. So notice here, I have a parent function again of an x squared. So this now, if we plug in some values, actually you probably did that in Algebra 1, Algebra 2, probably Algebra 2. What happens is that you would think you might have to go to the left by 2, but actually you're moving it to the right by 2. So this is my new vertex, and again, using those points for a parabola, we go over 1, up 1, over 2, and up 4, gives me those new points, and I can complete the kind of the 5 points there as a shift to the right by 2. Here, when I have a plus 1, you might think you go right 1, but when you're grouped with the x, it's the opposite of that. Take the opposite of what you see inside there. I actually have a shift of negative 1, over 1, up 1 from that new vertex, over 2 and up 4, and fill in the other 2 points, and that gives me that parabola. Okay, so generalizing this as a horizontal transformation, we're going to let f be a function and c a positive number. Then we have y equals f of x minus c takes the original graph, and we want to go to the right by c. So again, when you are grouped with the x, do the opposite, not a minus c, go plus c by c. And the graph of y equals f of x plus c takes the original left by c. Okay, so let's kind of look at these two with changing our graph set for our parent graph. Notice this first one, I have an absolute value, but I have a minus 4. That minus 4 is a vertical shift because it is not grouped with the x, so that means I'm going to go down by 4. Take that sign as is. When it's inside here with the x, that's when we have to go the opposite. So I'm going to go down 4. That's going to be my new vertex because recall the absolute value is a V shape. So it has a 1 in front. That is constituted as the slope. Up 1 over 1, up 1 over 1 gives me half of my V, and I kind of do the opposite to make it'll be a negative 1 slope going the other direction. Up 1 to the left 1, and so you end up having those points. There's my sketch for the absolute value of x minus 4. Now, notice I have a plus 3 underneath the radical with this. This is a radical equation where we have half of that parabola. So if we recall, this was kind of the original graph there. But what happens when I have that plus 3 grouped with the x? That is a horizontal shift, and that is the time that we have to take the opposite of that. So we're going to go left 3, 1, 2, 3. That gives me my new kind of end point here. Over 1, up 1, over 4, and up 2. Gives me those new points for that square root function. And our last one here, working with just horizontal and vertical shifts, is that we have x minus, whoops, I didn't do a function. F of x is equal to x minus 1 cubed plus 2. So that means this is going to take me to the right by 1, do the opposite, and this take as is. We're going to go up by 2. So over 1 and up 2, and this x cubed was that squiggle function. So part of it's going to be off the graph, but we're going to go over 1, up 1, over to the left and down 1. That gives me my little squiggle right here. But remember, we would go over 2 and down 8. 1, 2, 3, 4, 5, 6, 7, 8. So we're not too bad off here. I'm just going to, again, sketch it. When I ask for a sketch, I'm not going to be too picky, but you do want to be pretty accurate in some cases. You don't have to draw every single point, but get a good representation of that graph. All right, reflections over the x-axis and y-axis is where we're moving next. And we're going to try to look at the graph of f of x equaling negative x squared to see what happens. And so, if I had the points here of 0, 0, 1, 1, and 2, 4, what we have here with that negative in front, this was the original part. Basically, I got to take the opposite of that. So I have to take the opposite of the y. So, well, that one's going to still be 0, and that one's going to be a negative 1. This one's going to be a negative 4. So we're still going to have the same vertex, but instead of going up like the original parabola does here, we are now going to go over to the right and down 1 to negative 1, over 2 and down 4, and this will give us, again, 2 for 1 deal with these points. And what I have here is now an upside down u versus a right side up u. And so what we have is that the y coordinates end up being opposite of each other, making this a reflection over the x-axis. If that was my mirror, that would be my reflection. So the graph of y equaling negative f of x reflects the original graph over the x-axis. Now, okay, very good. All right, so what happens if the negative goes inside the function? We have inside the function. Now, this one we got to be careful with because we can only take the square root of a positive number. So if this is negative inside here, then this must be negative in order to make it a positive. And what happens with this one is that the x coordinates end up being opposite of each other, making this a reflection over the y-axis. So the graph of y equals f of negative x reflects the original graph over the y-axis. So what happens here on this? The original t-table for a square root was 0, 0, 1, 1, 2, 4, 2. So what we're going to do is we're going to multiply the x value by negative 1. This still becomes 0, and this becomes a negative 4. So what happens with that, my ending point is still going to be here, but instead of it going this way, we're now going this way, reflecting it over the y-axis. So over 1 and up 1, over 4 and up 2. Make sure you go in the right direction, that you don't get it confused with slope, where you have to go in the y direction first over the x. So that would be my graph of negative x underneath that radical. Okay? All right, very good. Let's turn to the next page and see what happens on these reflections. So if I have f of x equaling negative of the absolute value of x, well, the original looks like this. So I'm just going to reverse that over the x-axis because it's out front. So I'm going to have vertex at 0, 0. I'm going to have this as the right side and this as the left side. There's your negative absolute value of x. Now, if I have the cube root of x, let me remind you what it looked like. It looked like something like this. And so basically we're going to reflect that, because it's on the inside, we're going to reflect that over the y-axis. So basically we're still going to go through 0, 0, but this point right here, instead of it going over the y-axis, would now be this point. And this point would now end up being this point. Okay? And this point of 8, 2 is now going to be the point negative 8, 2, which would be about there, and this one is going to be about there. So what you're going to have with it being over the y-axis is something that looks like that. So that one's a reflection over the y. And this is a reflection over the y. Now, this one actually has a horizontal shift, vertical shift, and a reflection. So this is reflection over the x-axis. This, take the opposite of what we see with the x, is going to be left 2, and this is take as is. We're going to go up 2. It is an absolute value, so it's going to take on the shape of this V over here. So we're going to go negative 2 up 2. And instead of going up like this, now we're going to go down like this. And again, we haven't changed any of the slopes yet. We're about to do that with our scalings, but at this point, we still just have a slope of 1. Okay? All right, our next transformation has to do with y equaling c of f of x being scaled vertically by a factor of c. Okay? So, notice here we have this graph of 2x squared. So if you remember the original points, 1, 1, and then 2, 4, what happens here, this is the x squared that I have right here, but if I have 2 times that, now all these values get doubled. So when I multiply by 2, I get 0, 2, and 8. So some of my students like to do this so that they just know exactly where to go. So we're not going to go left or right, up and down, because there's no plus or minus within there, so we're still at a vertex of 0, 0. Instead of going over 1 and up 1, now we're going to go over 1 and up 2. The matching point would be over here at negative 1, 2. Then we're going to go over 2 and up 8, which is about there, which the matching point would be about there. So what I have is this parabola that's a little bit skinnier than what we had originally. And likewise, if I have this with a 1/2, 0, 0, 1, 1, 2, 4, I'm going to take all my y values and multiply them by 1/2, so I get 0, 1/2, and a 2. So when I do that from the original origin, which we're not moving left or right with any vertical or horizontal shifts, we're going to go over 1 and up 1/2. Matching point would be here. Then if I go over 2 and up 2, then I now have these points. So in a sense, we've kind of squashed down our parabola a little bit, made it a little bit fatter than what we had with this more skinnier one with any number greater than 1. So you'll see that anything between 0 and 1, you will have a kind of a vertically compressed parabola. This one would be a vertically stretched parabola is what we say. So we're going to let f be a function and c a positive real number. If c is greater than 1, which would be this case over here, the graph y equaling cf of x is vertically stretched by multiplying each of the y coordinates by c. Vertically stretched. That's important for you to remember that piece. And if we are in between 0 and 1, 0 is less than, not equal to, less than c, which is less than 1, so we're in between 0 and 1, then the graph y equals c times f of x is vertically compressed by multiplying each of the y coordinates by c. That's exactly what we just did. Okay. Now, that's if we have a number on the outside. The most hardest one, I think, is the one where the factor is scaled on the inside. So the last transformation has to do with y equaling, let's go, f of cx, squeeze that, being scaled horizontally by a factor of 1 over c, okay? So this is going to be really, really important that you watch the terminology here. So we're going to let f be a function and c a positive real number. If c is greater than 1, then the graph of y equaling f of cx is horizontally compressed. It's kind of opposite of the other one too. Horizontally compressed by dividing each of the x values by c. Now we're not multiplying here by c, we're dividing the x values by c, so everything's kind of switched up a little bit. If we are between 0 and 1, then the graph y equals f of cx is horizontally stretched by dividing each of the x coordinates by c. That's where that factor of 1 over c comes into. So you multiply by 1 over c or divide by c. Either way works. So I have this graph here, and this is another way that sometimes we look at things and being able to change things. We do have these points, negative 2, 0, 0, 3, 4, negative 3, 2, 0, 6, 0, etc. And I want to figure out what g of x is if I have that 2 on the inside. So remember, that means I need to divide each of the x coordinates by 2. So since it's greater than 1, we're going to have a compressed graph. So this is what I like to do. I like to just write these points down. Negative 2, 0, 0, 3, 2, 0, 4, negative 3, and 6, 0. And if I have to divide each one of those x coordinates by the c value, there's c, it's 2, then this now becomes negative 1. This becomes 0 still, that becomes 1, that becomes 2, and that becomes a 3. And now I can just plot these points and connect them. So negative 1, 0, 0, 3, 1, 0, 2, negative 3, and 3, 0. So if you can kind of tell, maybe we do it on the same graph for you to see, this is more compressed, like an accordion. It's squashed in like an accordion, more so than what the original was. Now, same way on this function, now I have 1/2. So that means that if I divide by 1/2, if I divide by 1/2, that's the same as multiplying. I'm just putting the original points down here. Same as multiplying by 2. Dividing by 1/2 equals multiplying by 2. So therefore, this is going to be negative 4. This is still going to be 0. This is going to be positive 4. Then I get 8, and I get 12. I'm still going to be off the grid. But we can see how we kind of basically horizontally stretch it like an accordion this time. 0, 3 would be here. 4, 0 would be here. We end up having 8, negative 3, which would be about here, and 12, 0 is approximately there. So if I look at that original graph, then I end up getting something that looks like that. So being able to, not even knowing what the function is, but having a graph of it, you can still do these transformations as we have done before. So let's move to the last page on this marathon section of 1.2. I promise they'll get shorter. Next one on trig is much shorter. All right, so here's another one of these graphs. Let's see if we can do this transformation on it. Let's see if we can do this transformation. Then we'll do some of our parent functions. So, what is the transformation here? If I have f of x plus 1, that's a plus c inside there. That was the horizontal shift where we're going to go left by 1. And this one we're going to take as is, so we're going to go down 2. So every point, we're going to go left 1 and down 2 to get our new point. So the first point is negative 4, 0. We're going to go left 1 and down 2. That gives me that new point. The next point is negative 2, negative 2. Go left 1, down 2. Then we have the origin. Left 1, down 2. Then we have the point 2, 2, which is right here. Down 1, or left 1 and down 2. And the point 4, 0, left 1 and down 2 gives me this one. So basically, we've just moved it over once and shifted everything down twice. And that would be my new graph. Okay? Now, with this transformation, we have a 1/2 on the outside. That means we are multiplying our y values. I don't like that with that x. We're going to multiply y values by 1/2. And you can even just throw the negative in there as well. This is going to be a reflection of the x-axis when it's on the outside. But you could also intuitively put that within here. So, let's do this. Let's write out each one of these points. Negative 4, 0, negative 2, negative 2, 0, 0, 2, 2, and 4, 0. So if these are my points, let's go ahead and just multiply by a negative 1/2. That still gives me 0. Multiply by negative 1/2 gives me a 1. This still gives me 0. This now gives me negative 1, and that gives me a 0. So negative 4, 0, and instead of going down first, we're now going to go up. So negative 2, 1. And 0, 0, 2, negative 1, and 4, 0. So what we have done is not only vertically compressed that, but also reflected it over the x-axis. So if they ever ask you to describe what happens to it, that one would be vertically compressed and reflected over the x-axis. All right, so let's do these functions here. Two things that happen for this example. The negative out front is a reflection over the x, and this negative 2 inside tells me I'm moving to the left 2. Now this is the parent function of x squared, which is our parabola. So that means that if I go left 2, that's where my new vertex is, and instead of it going up, we're going to reflect it over the x. So it's going to go down. What are the key points? Over 1 used to be up 1, now over 1 and down 1. Over 2 and down 4 in this case. Do a 2 for 1 deal with your points. And we get that nice upside down U shape. Here I have 2x squared minus 4. This now is a vertical shift down by 4. And here I have a 2 on the outside. That is not on the inside of my function like a square root or something like that. This is actually going to be a vertical stretch. Vertical stretch by 2, where we are going to multiply the y by 2. So if I have a parabola with that x squared, 0, 0, 1, 1, 2, 4, if I multiply by 2, these are the values that I get. But I also need to shift it down by 4. So the original vertex is going to go down by 4. Then we're going to go over 1, up 2, over 2, and up 8. Over 1 and up 2. Match that point. Over 2 and up 8. This gives me 4. 4 more gives me an 8, so I'm here. This again, is one of those vertically stretched parabolas. All right, square root of x minus 1 plus 3. Underneath here, I've got it grouped with the x. Take the opposite of what you're looking at. It's going to be that horizontal shift to the right of 1. This one take as is, so we're going to go up by 1, up by 3. For the original square root, 0, 0, 1, 1, remember we switched the points of a parabola because they are inverses. And we're going to now be at 0, 0. Whoops, that's the original. I didn't shift over, or up, over and up. Okay, so from the original 0, 0, we're going to go over 1 and up 3. So this is kind of our new spot. So from here, I'm going to do this. I'm going to go over 1 and up 1. And I'm going to go over 4 and up 2. Gets me right there in the corner. And I'm going to do that half of a parabola, which symbolizes our square root. All right, 4 more. We've got this. All right, this one gives me a -2 absolute value of x minus 2. Inside here is a horizontal shift. Do the opposite. So we're going right by 2. This tells me I have a reflection over the x-axis with it being on the outside. And the 2 tells me there that I'm going to be vertically stretched on that case. So make sure you know what happens in each case. So I'm going to move the original 0, 0 over by 2. Remember that was a v for an absolute value. Now remember on an absolute value I also told you the number out front was dealing with the slope of that. So it is true if I go up 2 and over 1. That gives me kind of a new point. Oops, but we're not going to go over 1. We have to reflect that. So just a 2 out front with no negative would do something like that. But we're going to go the other direction. So we're going to go down 2 and over 1 gives me that. Down 2 and over 1. And if I do the other side, down 2 over 1 this direction, it gives me this. So it's actually going to be kind of a little squashed or a little bit skinnier of an absolute value. All right, x cubed is our parent function here. If you recall, we had -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. These t-charts on these parent graphs are really, really important for you to do a sketch of. This number out front is a vertical stretch by a factor of 1/4. So that means I'm going to take the y value and multiply it by 1/4, which would give me a -2, a -1/4. That still stays 0. Then we get 1/4, and we get a 2 there. So if I were to plot those points, -2, -2, then we have a -1, -1/4, which is about there. Then we have 0, 0. Then we have 1, 1/4, and 2, 2. With that value being between 0 and 1, remember that was our vertical compression. We squashed it, okay? So it's a vertical, oops, I said vertical stretch. That should be, whoopsie, vertical compression. Because it is less than 1. All right, same way here, we have a vertical compression. Vertical compress. Then we are going to the right by 2, take as is, down by 1. So the original 0, 0, we go over 2 and down 1 gives me that new piece there. So if you wanted to do a T-chart here, -2, -8, -1, -1, 0, 0, 1, 1, 1, 2, 8. And we want to multiply everybody by a half. Now that gives me a -4, -1/2, a 0, +1/2, and a 4. So from there, you can easily graph those. So doing a little bit of work on the side sometimes helps out. Oops. I didn't do my shift. Okay, so from here, where we over 2 and down 1, we go over 2 from there and down 4. 1, 2, 3, 4 would give me this point. Over 1 and down a half would give me that point. To the right of that by 1, up a half, and then over 2 from what we call the point of inflection, over 2 and up 4 gives me this point right here. And so again, this is kind of a vertical compression. You don't see it as much as the last one, but it does work as well. All right. Last one. Last one is a cube root. So a cube root was one that went sideways. It had a little squiggle in it, but this time we're going to move to the right by 1 and up by 2. Again, take the opposite of what you're looking at. Take this one as is. So if I go over 1 and up 2, that gives me this point. So going from kind of the originals here, there's no compression or anything like that. I'm still just going to go over 1 and up 1, down 1 and over 1. And then from the turnaround point there, we're going to go out 8, which would be at 9 and up 2. And then out 8 more gets us to -7, and down 2 gets us back down onto the axis. So this is going to give us that cube root function. And that, ladies and gentlemen, is the end of our marathon section 1.2. I'm telling you, there's a huge amount of information in section 1.2. Multiple chapters of an Algebra 2 or a college algebra class packed all into one. But I wanted to give you as much information as I could for you to kind of go back and review. So if you have any questions, please let me know. But if you don't, we will see you next time.